Hi, I'm Seth Messer, this is Sly Rahimi, and this is Professor Paul Granis, a physicist here at Stony Brook University. He was just part of a large team of 430 physicists working on a project to prove the existence of the top quark. What was it like working as part of such a huge team?
Well, it sounds like a large number of people, but there are many, many jobs that need to be done. So you build this detector, you build that detector, you build this software, you put together the selection of events, you do the analysis on various things, and each of those teams tends to be 4, 5 people. And so although the collaboration is large, the individual working relationships tend to be a finite size, more like other science.
So what particular field were you responsible for?
At the time, I was in charge of the full collaboration. And so I organized the teams, reviewed all of the results. We built the detector under my leadership. So mine was, in a sense, the coordinating and driving role for these studies.
Was there ever an issue with communication in between teams?
Well, that is certainly an issue. If the communication isn't good, then things fall apart. Each individual person, although on a particular project works with 3 or 4 others, will have several projects going on. And in the other ones, he's working with somebody else, and so there's interconnections. There are very frequent meetings of larger groups that bring together individual studies and projects, and quite frequent meetings of the full collaboration where things are discussed. So yeah, we work a lot on that communication and documentation of what we've done and criticizing each other's work. There's a lot of that. I mean,
Wow.
bang on the results from any particular study quite critically.
So from beginning to end, how long did you say this entire endeavor took?
Well, the experiment started in 1983. It was approved. In 1992, we had finished building the detector. It was a big 5-story high piece of apparatus, and started taking data. We ran with that set of apparatus, those detectors, until 1996. We went offline for 4 years and built an upgrade of a lot of things that were new. And from 2000 until 2011, we ran again, pretty much continuously. In 2011, the Tevatron collider shut down. And since then, we've been analyzing the data that we finally acquired and updating previous results and so forth. So from start to finish, it's been 32 years.
And it's still continuing to this day.
We're winding down.
So you were still sifting through the data that you've collected.
That's right, yeah.
And as you were explaining to us before this interview, nothing exciting or new has yet come from the data.
Well, the discovery of the top quark was, in a sense, new.
Yes.
And exciting. There have been new and very interesting results in other sectors. Insofar as the top quark, its properties agree very well with the theoretical framework that we have. So there's not been any splashy news.
Right, so basically what you're saying is the discovery of the top quark kind of let the standard model fall into place to where we already believe it is. So it just kind of gave us extra confidence that we're right about our preconceived theories.
Yeah, it conforms to the standard model. We're upset that we haven't seen something new because we think there should be something.
You had said that other sectors found things. Care to elaborate on that?
studied the properties of mesons, which contain bottom quarks. And one of those should have an oscillatory phenomena behavior that what's called the B quark can turn itself into an anti-B quark and back again, and
Right.
does so very rapidly.
Right.
And the speed with which that happens tells you a lot about the presence of new physics. So we measured that oscillation finally.
What do you call that? What kind of frequency is that?
Oh, it's
It's not its spin, is it? It's
no, it's an oscillation from a particle to an antiparticle and back again.
That's so strange.
And the frequency is very high. In terms of the distance that it has to go before it's turned from one into the other is a few microns, which is
Very, 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 very
is
small.
small. So a micron is 10 to the minus sixth of a meter.
Right.
So
Wow. Wow. All right. So throughout the entire process, you were bound to encounter difficulties and obstacles. So could you describe some of them? Was it people? Was it apparatus? Were there malfunctions that you experienced?
Oh, there were countless obstacles. I mean, just bringing together a collaboration to build this detector and to design it and to do all the work that was necessary was a huge job. And we started 4 years later than our competitor, friendly competitor at the Tevatron.
Mm.
So we had to catch up. Fortunately, the accelerator didn't produce a lot of collisions until after we had finished, and so the timeline was not important. I'll give you one example of an obstacle that we found. There were chambers that recorded the passage of muons that penetrated through all the material inside of the detector and finally emerged into the outside. And these detectors had a gas in them, and they had electrodes buried inside to collect the charge. And the particular combination of the electrode material and the gas meant that there were chemical deposits after a while that coated the anodes, the collecting electrically charged wires that were in there.
Mm.
And so basically it built up crud and made the chambers go dead.
Oh, okay.
Because the current wouldn't flow anymore.
Yeah, that is insulating, in fact.
Insulating sludge.
And it was hard. I mean,
So how'd you get around that problem?
So, I mean, and we had acres of these chambers. We couldn't take them all apart and replace the electrodes.
And you'd have to probably do that over and over again.
And you'd have to do that over and over again. We found this fairly early in the run, and so the lifetime was short, and it was proportional to the amount of current that was being delivered by the accelerator. So there was a fix that was found, which we called zapping. And we applied a short pulse of high voltage to these wires that had the crud on them, and shocked that coating such that it cracked and fell off and collected at the bottom of the chamber.
So
That's a
basically
great
like
idea.
vaporized it.
Yeah, it vaporized it.
That's a great
Vapored
idea.
or cracked it, I'm not sure what it did. It came off in pieces.
Okay. So did you adjust the previous data that you had beforehand, or what did you end up doing with that data?
Well, I mean, what happened was that slowly over time, the efficiency of these chambers went down. And so we corrected for that in the analysis. We said, okay, well, we know what that efficiency is.
Based on the rate of...
You just fold that into the calculation. So you could run with the data, but after a while, the efficiency approached zero, and you have no data.
Yeah, I mean, yeah, then it just stops.
Yeah.
So you just had to keep cleaning it after, probably, yeah.
Yeah.
Dang.
And part of that upgrade that I mentioned from 1996 on was replacement of those chambers.
What'd you replace them with?
Different materials, different gas.
Things that didn't sludge up.
Yeah.
Probably smart.
But still, you went on for around 13 years like this without upgrading?
No, we went on 92 to 96, so the first round was
Even so, 4 years.
4 or 5 years, and we discovered this problem about halfway through, and so we zapped the chambers, and maybe we zapped them one more time, and then they survived until we replaced finally.
Okay. It's interesting. So how did you get involved in such a project?
Originally, there was a machine, a collider that was going to be built at Brookhaven Lab.
Right.
That machine finally was cancelled. It re-emerged as the relativistic heavy ion collider. The tunnel and the infrastructure was then used for that. So we had a proposal for a similar but smaller experiment at Brookhaven. There was then a call for a second experiment at Fermilab, and we said, well, why not? We could propose more or less the same thing there. And Fermilab considered it, and there were a dozen proposals for the second area. And we basically had a shootout, and there was a committee to evaluate all these proposals, and they finally said, we don't like any of those proposals all that well. And they asked me to go away, form a collaboration, do something more ambitious. So that's how we got into this.
So, was it your idea to research the top quark?
Well, I mean, ideas like that are all over in the community, so I mean, it was certainly known that this was one of the things that you wanted to do.
What were some of the other choices on the board?
Oh, the experiment did many, many things. We had 6 broad areas of research, each of them with its own physics group and meetings and analyses.
Could you list them for us?
So top quark, the study of the electroweak bosons, the W and Z boson, the study of the strong interaction, it's called quantum chromodynamics, the study of the B quark states.
Flipping from the NTB to the B.
And so that was a piece,
Right.
that was one of the aspects of that group's work. There was a group that was devoted to looking for new phenomena of whatever sort. The thing that we think is out there that tells us that the standard model is not complete.
Right.
So we searched, half of our papers were search for this, search for that, search for the other. And all of them concluded, didn't see it. And the 6th group was the search for the Higgs boson, the 6th group. And we came very close. We had evidence for the Higgs at the time of the discovery at CERN. We had evidence in the channel where it decays in its most.
You never observed it?
We didn't.
Or
The
detected?
words evidence and observation or discovery have come to have rather specific meanings. So you ask yourself, what is the probability that the known processes, the backgrounds, can fluctuate in your measurement to mimic the signal that you saw? If that probability corresponds to 3 standard deviations, so the 10th of a percent or whatever
Right.
that is,
Up to the 1000th place, right?
you are allowed to call it evidence.
Okay.
Because it's unlikely, but it can happen.
So it's unlikely that it's just a random fluctuation.
It's
in
unlikely,
space.
but after all, 3 standard deviations, it
Very
happens. And if you make
specific.
enough measurements, one of them will have that kind of deviation.
Right.
Discovery requires a 5 sigma deviation from the background expectation, which corresponds to a probability of a few times 10 to the minus 7. A little bit more than 1 million, but a little bit less than 1 million to 1.
Wow.
So that's the standard that is
So that's what
chosen.
warrants discovery is
Yeah.
just very, very, very low uncertainty.
Very, very low probability that known processes could replicate what you saw.
Okay. Huh. you have any more questions for him?
So how did you get into science to begin with?
Oh, somewhere along the way, I got interested originally in astronomy. I thought astronomy was really cool, and I always sort of thought, well, that's where I'm going to head. By the time I got into college and then graduate school, the problems that astronomy was dealing with didn't seem so interesting to me, the problems at the time. So I then got hooked on particle physics, where there seemed to be a lot of opportunities. So I sort of liked science. I wasn't dedicated to it as in grade school and high school. But I like math puzzles, and I like physics puzzles, so.
Makes sense.
Yeah.
So what do you plan on doing now with your research?
I have two main threads at the moment. One is I'm again leading the collaboration of the zero experiment in these final measurements. So we're trying to finish up our legacy measurements. So that takes actually a good bit of my time. I'm also interested in pushing a new accelerator which would collide electrons and positrons, accelerate them in a line, so it's a linear accelerator. You have
Huge matter-antimatter explosion.
Two beams opposing, focus them down to a few nanometers and collide them. And after that collision occurs, after the beams go through each other, you just let them go down and dump them in the earth and accelerate a new set.
Right.
So we've been working on that now for 15 years or so. There is an interest in building that machine in Japan, hosted by Japan. And so we're trying to understand whether or not there can be an international collaboration that would build it and use it. Unfortunately, it is expensive.
What would the point of such a machine be? Colliding matter and antimatter.
Well, it would offer, first of all, a very clean way to study the Higgs boson, much more incisive than what can be done at the Large Hadron Collider. And so again, you would look to see, does the Higgs boson conform to this standard model picture, or is there something new? In top quark physics, it would make very much more precise measurements. And in particular, the knowledge of the top quark mass is important because it sort of dictates whether or not the universe is sitting in a stable potential well and will remain forever and ever, or whether it's unstable. It's in a little valley, but there's a mountain peak and then a lower valley somewhere else, which at least philosophically would be an odd thing if the universe were
A mountain peak.
not really a stable thing.
It would.
So this linear collider would aim at that. It would also be very incisive in studying anything new that is discovered. But if nothing new is discovered, then that piece is taken away.
Right.
So it's just going to help us answer questions about like the future of our universe.
So that's one, and also the critical question really is, what are the properties of this Higgs boson? Because they can dictate to us whether there's something new, and if so, what's its nature?
And how it
Which of
behaves.
the myriad possibilities seems to be chosen by nature?
Okay. I'd have to say, what do you think of the facilities we have now at Brookhaven compared to how it was when you first started?
Oh, Brookhaven was started many, many years ago. Started right after the Second World War. So technology has changed
Just a bit.
Unbelievably since then. So the facilities have grown. They have branched out. little accelerators accelerating protons and banging them into targets and seeing what came out. Now that's expanded to colliding these heavy ions, making quark-gluon plasmas. A very strong program in nanoscience and the new light source that is being built there to study the properties of materials. That's all new. So, yeah, but that's
Right, because I remember
70 years on, so that's
yeah, because I was visiting the facilities over the past summer, and I was just thinking, like, it seems a bit grandiose than its original purpose. So I was
Sure.
thinking, yeah.
But if you don't evolve and attack the questions that are of current importance and build new machines that extend your reach, then the lab will die. And there have been labs that died.
So going back to the international collaboration, how do you feel personally about it? Do you think it would be a viable option, or what would you feel about it?
Well, it's obviously viable because these large collaborations are all international. D0 was half US and half foreign. The LHC experiments, the largest contingent is the US, and it's about a quarter, 20%, and the rest scattered around the globe. So they are that way. The strange thing is that they work, and that people can communicate well enough, can cooperate well enough. As one example, one of the groups that joined the D0 experiment recently was from the Ukraine. They are working on a variety of projects in very close collaboration with Russian colleagues. Well, that's sort of cool because meanwhile, Russia is taking over Crimea, and
it's good to know that they can still get things done scientifically.
We have Pakistani physicists and Indian physicists who work together, and so forth and so on. So at the level of scientific cooperation, these
differences
national
are set aside.
boundaries don't rear their head.
That is really
very
cool.
strongly.
So how did you feel when your experiments actually ended?
Then you start holding parties and
Did you immediately want to start sifting through the data, or did you just want to take a breather and let your head cool down before you got on it?
No. The collaborations are big enough, and we collected data over a long period of time, and so the analyses were going on all the time.
Okay.
I mean, it wasn't wait till it's all there
Right.
and then analyze it.
So you got a piece of data and started analyzing
So we were
it.
publishing 50 papers a year from 2002 onward, for example.
Wow.
40. And sometimes there was just redoing something that we had done before, but now with more data and better precision.
Wow.
Is there anything you would have done differently?
The name of the experiment, D0, is chosen because the accelerator has six similar segments and 6 places where the beams could collide. One of them is called D0. It's the D sector, the beginning of it.
That is the most probable place they collide.
Yeah, there's 6 such places. There's A0, B0, and so forth. So we were at, our address was D0. I wish we could have found it better.
Okay. So do you have any other questions?
No, thank you so much for your insight on how to be a physicist, and it's been extremely
Insightful.
Thank you so much.
Good. Well,
Alright, thank you very much, Mr. Grannis.
thanks for doing this, and I hope it's been a pleasure for you.
So